position vector, vector v. And then what is the magnitude of v? And then number 2, if w equals negative 4i plus 10j, first of all, I want you to draw w. 2, what's its magnitude? 3, what's the magnitude of 8 times w? And what's the magnitude of negative 8 times w? Good luck. Check your answers. I'll be up here momentarily. All right, go ahead and check your answers. I'll explain it momentarily. Alright, so a position vector has to start at the origin. And you notice that between negative 8 and 2, you went right 10. And then you went down 24, going from 5 to negative 19. So the horizontal component had to be positive 10. And the vertical component had to be negative 24. How we got 10i minus 24j. Now I wanted you to draw it just to re-emphasize the fact that a position vector has to start at the origin. Now for the magnitude, just use the Pythagorean theorem. 10 squared plus 24 squared equals r squared. Solve for r, you will get 26. Now for number 2. If w equals negative 4i plus 10j, you had to go negative 4 in the horizontal component, and then 10 in the vertical component. And I wanted you to draw it just to re-emphasize the fact that the position vector has to start at the origin. Now what is the magnitude? Well, use the Pythagorean theorem again. 4 squared plus 10 squared equals r squared. You'll get down to the square root of 116. Square root of 4 times the square root of 29, or 2 root 29. Now for 8w, remember, it's just 8 times whatever w was, the magnitude of that one. Well, we know that's 2 root 29 from right there. And 8 times 2, 16 root 29. Well, then what's the magnitude of negative 8w? Well, remember, the negative only changed direction, did not change magnitude. So, it's still 16 root 29. I want to show you what we've really been doing. Because so far, we've looked at how to geometrically interpret vectors, and kind of how to interpret vectors algebraically. Today we're going to look way more into how to interpret vectors algebraically and how we can combine them algebraically also. Now, we already combined geometrically. Don't worry about writing this part down, just follow along with me. That's what I'm worried about. So, we notice v is going right 1, 2, 3, 4, 5, and up 1, 2. So if I have to write a position vector for v, imagining that that's the origin, it'd be v equals, we just said right 5. So 5 and up 2, 1, 2. Or, that'd be 5i, because that's the horizontal component, plus 2j, because that's the vertical component, the equals. And then w. Well, if you have to write a position vector for w, well, imagine this to be the origin. It'd be right 1, 2, and up 1, 2, 3. So w would have to equal right 2 and up 3, or 2i plus 3j. Now, I want to look at how we can combine vectors, but we already did it geometrically. I want to see if you can connect how we do it algebraically. Well, geometrically, if we want to do w plus v, remember, we're going to start with w and graph w and then put v on its terminal end. So w was right 1, 2, and up 1, 2, 3. So if we think about it, right 1, 2, up 1, 2, 3. There's the end of w. Then this is plus v. So we got to put v on its tail end. Well, v was right 5 and up 2. So right 1, 2, 3, 4, 5, up 1, 2. And there's v. And then remember from before that w plus v is when we connect the dots. So this part is w plus v. Now I want to take a look at that position vector, pretending this is the origin for a second. If this was w plus v, well it is, and pretend this is the origin, well let's look at how much we've gone. We've gone right 1, 2, 3, 4, 5, 6, 7. So we've gone right 7. And we've gone up 1, 2, 3, 4, 5. Which in ij form would be 7i plus 5j. Now here's the interesting part. I want to see if we can figure out how you could come up with 7i plus 5j. From like, I don't know, the 5 and the 2. and the 2 and the 3. So if you look at it, it appears that you're able to just do this based off of component-wise thinking, which I described last time. If you look, the horizontal component and the horizontal component made the horizontal component of the combination. The vertical component and the vertical component made the vertical component of the combination. So it looks like this is what's happening. Let's just double check for multiplication. Because multiplication is different than addition. So let's make sure it's working there also. So let's take a look at 2v. If I wanted to draw 2v, well, we know from before that, well, we need to draw v and then add v to it again. Well, v, remember, was right 5 and up 2. So right 1, 2, 3, 4, 5, and up 1, 2. V. And if we want 2v, we need to add v to this again. Well, v was right 1, 2, 3, 4, 5, and up 1, 2. Well, then for 2v, if we think about it, it's right there. And then 2v would have to be, well, we're going right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going up 1, 2, 3, 4. Or 10i plus 4j. Now think about that for a second. Over there, you know that v is 5, 2. Well, 2v, multiply the horizontal component by 2, gave you the 10. Multiplying the vertical component by 2, gave you the 4. So it looks like we can just do this based off of what's called component-wise thinking. So now we're going to take a look at algebraically combining vectors, which is done purely through component-wise thinking. Now the first thing I want you to notice, as you're copying this down, is the directions. Find each quantity if. Well, in example 1 and 2, both say find each quantity. Meaning that we're going to find a vector here. Or we're going to find a vector that looks something like in that form. That's different than if you look in the past days notes in your practice problems where it says draw the vectors. Or draw the vectors. That's the big one. If you're drawing vectors, that's geometrically combining. And that's what you were doing before. Now find each quantity if v equals 3, 5 and 6, negative 2. Now the first one is v plus w. Well, for v plus w, we've got to think about this. Well, v is 3, 5, and w is 6, negative 2. Remember, we do this based off component-wise thinking, meaning that I'm going to look at the horizontal components and add them. I'm going to look at the vertical components and add them. So I'm thinking that v plus w equals, well, 3 plus 6, which is 9. And 5 plus negative 2, which is 3. Well, for v minus w, still doing it component-wise. The horizontal component of v was 3 minus the 6. That's going to be negative 3. Comma. Well, it's 5 v minus negative 2. 5 minus negative 2 is 7. And I promise if you graph those, you would have gotten the same thing. Let's put the right symbol there. There we go. And then for 3w, well, remember from what we just did before, all we got to do is multiply each component by 3. Well, w was 6, negative 2. So 3w is going to be 6 times 3, 18, comma, negative 2 times 3, negative 6. Take a second and copy down example 2. Why not put down the pen? Alright, so this time everything's in ij form. Same idea though. We know the number in front of the I is the horizontal component, and the number in front of the j is the vertical component. So we still add things component-wise. But here's what I do. It says 2 times b. So I figure out, well, b is right there, times 2. So in reality, this part is really negative 16i plus 12j. Because I multiplied the b vector by 2. I got negative 16 and 12. And then for 5 times the d vector, well, if d was negative 10, negative 22, well, 5 times negative 10 is negative 50i minus, 22 times 5 we're thinking about negative 16 plus negative 50 is going to equal negative 66 I. And then, well, if it's plus 12j and minus 110j, that's going to come out negative 98j. We're done. All based off of thinking about this component-wise. Now, for the next one, 3g minus 2d. Let's do the same thing. Figure out what 3g is. Well, 3 times the vector g is going to be 27i, because I multiplied the 9 by 3, minus 9j, because I multiplied the 3 by the 3. Then I know I'm going to have to subtract it from whatever 2d is. Well, the d vector is right there. So this one is negative 20i minus 44j. Then I have to think about subtracting these. And I have to do it component-wise. So I'm thinking 27 minus negative 20. So minus negative 20, that's going to be a plus, and that's going to be 57i. And then negative 9 minus negative 44, I'm thinking that's going to come out positive 36 plus 36j. That should be a j. I apologize, guys. You probably got that and you're saying something. And we did this by component-wise thinking. Now for the last one, 5b plus 10b minus 7g. I'm still doing this component-wise. So I'm thinking 5b. Well, 5 times b is going to be negative 40i plus 30j. And then for 10d, well, let's see, d is negative 10i, so that's going to be negative 100i minus 22, negative 220. J. And then for 7g, well, go to g and multiply it by 7. So 9 times 7 is 63, so that's 63i minus 21j. And then honestly, guys, I take it one step at a time. I do the plus first, and then I do the minus later. So I think negative 40 plus negative 100 is negative 140. I. Positive 30 minus 220 is negative 190j. And that covers the first two. But I still got to subtract that guy. So I'm thinking minus this guy. 63i minus 21j. Let's think about it. Negative 140 minus 63 is going to come out negative 203. I. And then negative 190 minus negative 21, well, that's really a plus. So negative 190 plus 21, it's going to be negative 169. And we did that all based off of component-wise thinking. So just to reiterate what's happened, if you have to multiply a vector, multiply a vector. That's why they're scalars. But when we combine, we have to combine component-wise. So the i's get added with the i's, the j's get added with the j's. It's a lot like combining like terms, except you're thinking about this horizontal component and vertical component. Same idea over here. You added the horizontal components, you subtracted the horizontal components. You added the vertical components in part A, and you subtracted the vertical components in part B. And so you try. Find the quantity if f is 3.7, g is negative 6, comma negative 10, and h is 20, comma negative 1. I want you to find 2f, negative 3g, f plus g, g minus h, 2f plus 5g, and 2g minus 5h plus 10f. Good luck. Alright, go ahead and check your answers, please. A and B should have been pretty simple. Just multiply the vectors by their scalars. Times 2 times negative 3 in this case. For C and D, make sure you did it with component-wise thinking. You should be adding both of the horizontal components and both of the vertical components of F and G. You should have gotten that. And then for here, you should be subtracting the vertical components and the horizontal components. Well, you should get negative 26 and negative 9. Now for E and F, a little bit more complicated. For E, you need to multiply F by 2 and G by 5. And then add their horizontal components, add their vertical components. Well, if you go 6 plus negative 30, it's negative 24. And if you go 14, it's negative 50, that's negative 36. Incorrect. Make sure you multiply G by 2, H by 5, and F by 10. You'll get these three vectors. Make sure result. So negative 12 minus 100 is negative 112. Negative 20 minus negative 5 is negative 15. Then we got to add it to 30 and 70. Well, negative 112 and 30 is going to make negative 82. Negative 15 and 70 is going to make 55. So we did this all based off component-wise thinking. Alright, so next big topic we're going to talk about is what unit vectors. If you remember from your notes a couple days ago, unit vectors were just vectors with the magnitude of 1. Now for any vector v, the unit vector, that is a u, going the same direction as v, is given by the unit vector equals, this v stands for the original vector, divided by its magnitude. Now let's talk about that for a second. We want to find a vector with magnitude 1. Well, notice that the direction doesn't change. So it makes sense that we're going to divide by the magnitude because it's not going to change the direction. We want the direction to stay the same. But we need to change the magnitude to be 1, so divide by the magnitude. Example 1. Find a unit vector in the same direction as v equals 8, 6. First thing, go ahead and graph it. It's 8, 6. We can go out 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Now why am I doing this? A, to find the magnitude. Remember how we did that? We graphed it, we made a triangle, and we used the Pythagorean theorem. That's what helped us. Now if you look, you went out 8, and you went up 6. So you went 8 squared plus 6 squared equals r squared. That's 64 plus 36 equals r squared. Which means 100 equals r squared. Take the square root. That means 10 equals r. So we know that the magnitude of v is equal to 10. So now we just got to go back and do this formula. Well, it says the unit vector is the original vector divided by its magnitude. A very common way you will see that written is instead of written like that, it'll say u equals 1 over the magnitude, which was 10, times the vector, which was 8, 6. So just to reiterate, it was much more like 1 over the magnitude times d. And that makes the same thing by how fractions work. So, distribute the 1/10 to the inside. Think about it that way. Then you got 8 over 10, 6 over 10. Yes, you need to simplify. 4 over 5, over 3 over 5. And you can double check me. The magnitude on this is 1, and when you graph it, it will be going the exact same direction. Go ahead and copy down example 2. Find a unit vector in the same direction as v equals 10i minus 4j. Start this the same way we started the other one. So graph it. If it's 10i, that means you're going 10 in the horizontal direction and negative 4 in the vertical direction. So out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and down 1, 2, 3, 4. Remember, we made our vector, made a triangle out of that thing. So for a triangle, we're going to go up here and across there. If we think about it, that was 10, and that was negative 4. So 10 squared plus negative 4 squared equals r squared. And so let's see, that's going to be 100 plus 16 equals r squared. Yes, I picked this on purpose. You have done this before, oddly enough, like 10 minutes ago. And that would be what? 4 and 29? So 2 root 29 equals r. So that's the magnitude of b. The magnitude of b is 2 root 29. So now we need to go back and we need to do this part. So we know that the unit vector has to equal 1 over 2 root 29. Leave it like that for now. We'll rationalize later. Times the vector 10 and negative 4. Let's, since it's in ij form, leave it in ij form. 10i minus 4j. Let's distribute and kind of cancel in the same step. If you think about it, when you distribute this, the 10 and the 2 are going to cancel and make a 5. So that'd be 5 over root 29i minus, and think about it, the 4 and the 2 are kind of going to cancel, pick a 2. So that would be 2 over 29j root. Yes, you need to rationalize your answers. But if you look, you want to multiply first because it's easier to rationalize this one than rationalize that one, then distribute and play with it. Just rationalize at the end. So times root 29, times root 29, same idea there, times root 29, times root 29. And then that will give you that the unit vector is equal to 5 root 29, root 29i, minus 2 root 29j. There you go. Final you try of the day. Find the unit vector in the same direction as d equals negative 8 comma 10 and d equals negative 5i minus 12j. Good luck. All right, check your answers, please. So I graphed both of them. Use the Pythagorean theorem. 164 is negative 8 squared to the positive 64 plus 100. That's 4, 41, 2, 41. Distribute and rationalize. You get that. And then for number 2, negative 5 squared is 25, negative 12 squared is 144, both positive. It's 169, square root 13. So then distribute the third 1 over 13 to both of them.